What if I told you multiplication can fail, but the numbers survive? Octonions are numbers that live in 8 dimensions. They are often called the final stop in the hierarchy of number systems. Beyond them, there is no higher dimensional structure that still deserves to be called a number system. But in octonions, multiplication is not commutative and not even associative. So why are octonions still accepted as numbers? Because they satisfy the last minimum requirement that any number system must have. Let's see what that is. To uncover what allows octonions to still be called numbers, we need to see how number systems gradually lose structure. In the real numbers, order, commutativity, and associativity feel almost obvious. But as dimension increases, algebra starts to fall apart. In 2 dimensions, complex numbers lose order. In 4 dimensions, quaternions lose commutativity. At every step, something breaks. And in 8 dimensions, with the octonions, even associativity collapses. Let's take a closer look at how that happens. An octonion has 1 real part and 7 independent imaginary units, so it is an 8-dimensional number. Associativity means this. No matter how we group the multiplication, the result should be the same. To check this, let us represent A, B, and C as octonions and verify it explicitly. But this multiplication is completely impractical because the amount of computation quickly becomes overwhelming. So instead, we use a visual tool called Fano plane. The Fano plane shows 7 imaginary units, E1 through E7. EK squared equals -1. There are 7 lines, including a circle. Each line has a direction. E7 times E2 means moving from E7 toward E2. And the value reached beyond that corresponds to the result of the multiplication. In particular, multiplying along the arrow gives a positive sign, so E7 times E2 equals E5. Against the arrow gives a negative sign. E2 times E7 equals -E5. Now, choose 3 units on the same line and do the multiplications. Both evaluate to -1. Associativity holds. Locally, the units lying on the same line behave like quaternions. Choose 3 units not on the same line, E1, E2, E4. Compute these multiplications. These multiplications are not the same. Associativity fails. So, in octonions, both commutativity and associativity are gone. And yet, octonions are still considered as numbers because division still works in octonions. I'll show you why. Here is an equation 5x equals 10. We can divide both sides by 5 because 5 has an inverse 1/5. Division works if every non-zero element A has an inverse A inverse, such that A times A inverse equals 1. Take a non-zero octonion A. All AK are real numbers. Define its conjugate. Multiply them. Remarkably, when the multiplication is fully expanded and simplified, all the imaginary parts cancel out. This is called the square of the norm. Since each ak is a real number, every term ak squared is non-negative. The sum can be 0 only if every ak is 0, which means a itself is 0. But we assumed a does not equal 0. Therefore, the square of the norm is strictly positive. Now, divide both sides by the square of the norm. So, what is this expression on the left? Since multiplying a by this equals 1, this must be the inverse of a. Therefore, every nonzero octonion has an inverse for multiplication. In this sense, division is always possible in the octonions. Many algebraic laws are broken, but octonions manage to preserve this final rule. They hold on to division until the very end. That is why octonions are considered as the last number system. Up to 8 dimensions, division survives. Beyond that, something more fundamental breaks. Not just the rule, but the idea of division itself. There exist non-zero elements whose product is 0. Can you believe that? Once that happens, division collapses completely. We'll explore what goes wrong in 16 dimensions in the next video. I'll see you there. Thank you.